Welcome to our next module of an intuitive introduction to probability, decision making in an uncertain world. The title of our new module is Discrete Random Variables and Probability Distributions. So let's dive right in. The concept or the name of random variable often confuses people. What is a random variable? It's actually a very natural concept that I'm sure you have used before. So let's start with an example. Recall the experiment of rolling two fair dice. We had an example a while ago, and what are the possible basic outcomes? There are all the possible pairs between the number on the first die and the number on the second die. So 1, 1, 1, 2, all the way to 6, 6. We have these 36 pairs of two numbers, and they're all equally likely. Often, however, we're not really interested in the pair, but we're interested in the sum of the pair if we play a game. And so then, what do? We just add the two numbers. The 1, 1 then is the 2. The 1, 2 and the 2, 1 are the 3. We have seen this before. And so what we are doing actually, by building the sum, we give to each basic outcomes a numerical value. And voila, that's already a random variable. Here's a technical definition. A random variable assigns a single number, a single numerical value to every basic outcome. Now, unfortunately, I have to introduce just a little notation. I usually try to avoid notation because I don't want to confuse students with notation, but here we just need a tiny little bit of notation. Usually random variables need a name, and unless we have a very good name from the context of a business application or some other real-world application, we use capital letters X, Y, and Z. Now, a discrete random variable is a random variable where we only have finitely many possible values, or perhaps infinitely many values, but values I can count. But let's now, for the sake of this module, focus on a list of possible values. So, with the sum of two dice, the possible values would be 2, 3, 4, all the way to 12. Now, we want to talk about probabilities. Here, with a random variable, we call the collection of the probabilities a probability distribution. It gives a probability to every possible value that the random variable can take on. Again, a little notation. What's the probability? We write P of X. Some people like to write PR for probability of X. Some people like to write P of capital X equal X. That may look a little funny to you, but what that means is the probability that the random variable X takes on a specific value, and that's then denoted by little x. I don't care which notation you use, but if you look at textbooks, if you surf the internet, you will most likely find one of these four ways to write down a probability. The next step then is sometimes we sum probabilities, and that gets us to the concept of a cumulative probability distribution. What the heck is that? Now, if I think of the cumulative probability of a number of the random variable, I want to add all the probabilities for numbers less than or equal to the number at which I'm looking at. Sounds a little complicated. Here, the notation would be probability that the random variable capital X is small or equal a particular value little x. Let's look at some example, and then I think it will be quickly get very clear. Back to our two dice. We had seen before the probability of a 2, that's just a pair 1, 1. There's only 1 out of 36 pairs that gives me a sum of 2, would be 1 in 36, 1 divided by 36. Then the probability that we roll a sum of 3 that's a couple 1, 2, or the other way around the couple 2, 1. So there are two possibilities out of 36. Probability 2, 36. And here you see a list all the way to the number 12. Now notice we cannot roll an 11.2. I cannot roll a pi, a 0, or a -5. All those numbers have a probability 0. Now let's return to the cumulative probability. Here, from a spreadsheet, I put together a table that shows us first, in the first column, the 11 possible values that the sum can take, 2, 3, all the way to 12. In the next column, the individual probabilities, 1 in 36 for 2, 2 in 36 for 3, 6 in 36 for 7, the most likely value, and then it goes down again all the way to 1 in 36 for the number 12. Finally, in the last column, we have the cumulative probability. What is the cumulative probability, for example, of a 4? That's a probability that we get a 2 or a 3 or a 4. So you see, f of x, therefore 4 is 0.1666, and so on. That's actually the sum of the 3 individual probabilities. Here's an easy rule. For the largest number, the f of x is always a 1. In this case, the largest number possible is a 12. So for sure, with probability 1, we will roll a number of 12 or less. Now, often people don't like these long Excel tables. They get too cumbersome, all these numbers, these many digits. So many people prefer a graphical representation of these probabilities. So here we have a graphical representation now of the individual probabilities. Again, we see all the numbers 2 to 12, and those are displayed here on the horizontal axis, the x-axis. On the vertical axis, on the y-axis, we see the level of the probabilities. You see the largest bar is at the number 7, and it goes all the way to 1/6, because the 7 is the most likely number when you roll 2 dice. You see then the nice symmetric form with the smallest probabilities for 2 and a 12. So these graphs of a probability distribution are very popular. Occasionally, you will also find graph of a cumulative distribution. Here, again, we go up in our numbers from 2 to 12, and we see that we get this type of step functions. That's very typical for the graph of a cumulative distribution of a discrete random variable. And we always see these steps as we hit the number 3, 4, 5, all the way to 12. Now, technically, I can also ask what's the probability I get a number of pi or smaller. Oh, I can look at this. Pi is between 3 and 4. So the bar in the graph shows me what the cumulative probability of that number is. Any number smaller than the smallest number possible, the 2, has a cumulative probability of a 0. And anything 12 or larger gets the number 1. Now, let me show you a different example that many of you may be familiar with, and that's the game of roulette. So, what in roulette happens is that there is a little ball that rolls around the wheel and eventually falls into a so-called pocket. Every pocket is connected to a particular number. Here, in the picture, I have a wheel as it's used in Europe with 37 possible numbers. There's a 0 and the numbers 1 through 36. In the United States, for example in Las Vegas, there are actually 38 pockets. There's a 0 and a double 0. Now, let's take this game of roulette and sort of describe it in the words of probability. Here we have a random variable, the possible values. Here I call the random variable R for roulette, and it has the possible values 0, 1, 2, all the way to 36. All numbers are equally likely. Quick aside, I know some pros may say, oh, the croupier may actually be able to game the ball a little bit and speed it up a little faster or a little more slowly to aim for a particular pocket. We don't think of that. We assume an absolutely fair game. That's a little side for the pros among you. So here now we assume that all 37 numbers are equally likely. This probability distribution is also called the uniform distribution. Here I wrote it down for you. We get the numbers from 0 to 1, 2, all the way to 36, and they all have a probability 1 divided by 37. Remember, the 37th number is 0. And now here we have a graphical representation of it. All numbers are equally likely. This graph looks pretty boring to me. It also gets convoluted. We have now 37 of these bars. So in the next lecture of this module, we actually want to go beyond these graphical representations. Maybe they're pretty pictures, but they're not always all that useful for us humans with our bounded mind to really grasp the uncertainty. And that will be the next step. So let me wrap up this first lecture of the new module. We learned about the concept of a discrete random variable. We then introduced the concept of a probability distribution, which really is nothing new. It's just a little bit of new terminology, giving probabilities to the numbers of a random variable. And we discussed the representation either in tables and graphs. Thanks for being with us at this lecture, and please come back for the next lecture. Thank you.